Welcome to the Sylow theorems. So let's go through section 2.5 on the Sylow theorems. Now we've classified finite abelian groups. We classified finitely generated abelian groups. In section 2.6 in the fundamental theorem of finitely generated abelian groups, any in particular finite abelian group is a direct sum of finite cyclic groups, which the result is applied to finite abelian groups. So now we'll turn our attention to finite non-abelian groups. We won't classify finite non-abelian groups as we did with the abelian groups, but we'll take some steps in that direction with the three Sylow theorems. It's unlikely that there'll ever be a classification of finite non-abelian groups. And the three results of interest are named for Peter Ludwig Sylow, who published these three Sylow theorems in 1872. We'll give a link to the paper down below. Like Abel, he was Norwegian. And as a little grammatical aside, in the US, it's common to pronounce his name Sylow, but I've heard it argued that in Norwegian, the more appropriate pronunciation is Sylav instead of Sylow. I'll stick with the US tradition of pronouncing it Sylow. All my classes, these were referred to as the Sylow theorems. In 1862, Sylow lectured at the University of Christiania in Oslo, Norway. In his lectures, he explained Abel and Galois' work on algebraic equations. So this is the very foundations of modern algebra in the sense of dealing with algebraic equations by applying groups and group theory. Between 1873 and 1881, Sylow, along with Sophus Lie, prepared an edition of Abel's complete works. Abel did more than just his algebraic results. And after proving Cauchy's theorem, we'll state Cauchy's theorem and prove it here shortly, that a finite group of an order which is divisible by prime p, that group has a subgroup of order p. Sylow asked whether this can be generalized to groups of orders powers of a prime p. The answer is yes, as we'll see in the first Sylow theorem. And these other two Sylow results are all contained in his 1872 paper. He spent most of his career as a high school teacher in Norway. He was awarded an honorary doctorate from the University of Copenhagen. And after that, he taught at Christiania University. This information is from the Mac Tutor History of Math website. Go to my online PDF notes, and this is linked to that very page. Okay, so the proof we're going to go through is very similar to the proof presented in Fraley's book in the senior level algebra class. I've stated here that Fraley mimics Hungerford. Actually, it might be the other way around because I think actually Fraley's first algebra book was in print before Hungerford's algebra book. But the developments are parallel. So whenever I state a result from the Hungerford book, I'll list the corresponding theorem number from the Fraley reference. And our first result of importance is the Cauchy's theorem. Let's actually read that. We'll go through the proof of the lemma and the theorem. But Cauchy's theorem says specifically, if G is a finite group whose order is divisible by prime power P, then G contains an element of order P. So this implies, for one thing, the existence of a subgroup, and the Sylow theorems are stated in terms of existence of subgroups. If there's an element of order P, then that element generates a subgroup of order P. Definition of order of an element, in fact. So it's not stated exactly as such, but Cauchy's theorem guarantees the existence of particular ordered subgroups. Okay, so let's look at the lemma, the proof of the lemma, on which Cauchy's theorem is based. Statement of the lemma is, if group H is of order P to the n, where P is prime, and this acts on a finite set S, and if S sub 0 is defined to be the X in set S, such that when H acts on S, it gives, as H acts on element X of set S, we get element X back, and this occurs for all H in the group. Then the claim is the cardinality of finite set S is congruent to the cardinality of set S sub 0 modulo P. Now, what we're dealing with here are X elements which are fixed under the group action. If we look at the orbit of element X, it only contains element X, the orbit under this group action, to use some of the verbiage from the previous section. So what set S sub 0 contains is, so actually this is how the proof starts, it contains all elements that have an orbit consisting of exactly one element, X itself. Recall the definition of an orbit was H acting on X as H ranges over the entire group. Group capital H is given here. We denoted that as X bar because we saw it was an equivalence class in the previous section. So an orbit contains exactly one element if and only if it's in X sub 0. So these are all of the orbit of cardinality 1 elements of set S. The orbits represent equivalence classes, so they partition set S. Equivalence classes on a set partition the set S. So set S can be written as S sub 0, these elements of X, those with an orbit of length 1, union X1 bar, union X2 bar, and so forth up through X sub m bar, where we're taking these X1 through X sub m's to be equivalence classes, X1 bar through Xm bar. We're taking these to be the disjoint equivalence classes of cardinality greater than 1. So all equivalence classes of cardinality 1 are represented by this set S sub 0, and these are the ones that have more than one element in them. So using a little dot inside the union symbol to indicate disjoint union, I believe we've done that before. So if we want to talk about the cardinality of set S, and we do, that's simply the sum of the cardinalities of these pieces. It was a partition, so it makes the counting easy. Now, the cardinality of equivalence class X sub I divides the order of the group, corollary 2.4.4.1. Let's go look that up and come back and finish the result. Corollary from section 2.4 is 4.4 part 1. Let's look back at that. Here's where we were dealing with those ideas. The number of the elements in a conjugacy class divides the order of the group. Group G in this case was represented in terms of an index, but we don't need that right now. So number of elements of a conjugacy class divides the order of the group. Of course, we had a finite group, or we wouldn't be talking that divides stuff. So that tells us that these things here divide P to the n. P is prime, so it must be that P divides the order of those orbits for each of the orbits, X1 bar through X sub m bar. So what we have then is a multiple of P, a multiple of P, blah, 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 a multiple of P. Cardinality of S equals a cardinality of S sub 0 plus all these multiples of P. I can drop that if we work modulo P and say the cardinality of S is congruent to the cardinality of S sub 0 modulo P as claimed. Okay, so a technical lemma to prove the following. If G is a finite group whose order is divisible by prime P, then G contains an element of order P, as stated. And remember, the importance of that is G contains a subgroup of order P. Well, the importance from the perspective of the Sylow theorems, maybe. Okay, this uses group action. It's not a real complicated proof. It's a little exotic, though, in terms of the group action, in my opinion. So we'll define S to be the set of P tuples of group elements with product E. P tuples, P coming from this prime introduced in the definition or in the statement of the theorem. And we're taking S then to be P tuples, so they're ordered. First one, second one, Pth one. P tuples of elements of group G, A sub I is in G, such that the product of those elements in that order equals the identity. In that order, because order matters, we may not have commutativity. With the order of group G equals n, so let's introduce parameter n just as a symbol to represent the order of group G. It was a finite group by hypothesis. We want to count how big set S is. Well, there's n choices for A1, n choices for A2, up through n choices for the second to the last of those elements in that P tuple. They could be anything. But the product of them must equal the identity. So there's only one choice for the last one. The last entry in that P tuple must be the inverse of the product of the first P minus 1 entries. So no constraints on P minus 1, the first P minus 1 terms, but then a constraint on the last term. So that tells us the cardinality of size S must be n to the P minus 1 power times 1. We know P divides G, the order of G. That was given. Order is divisible by P. P divides n in terms of this n parameter that we introduced to represent the cardinality of G. Then n is congruent to 0 mod P. We have let's see, P divides n is congruent to 0 mod P, right, from the fact that P divides n. And so, here's the algebra. We've taken something that's 0 mod P and raised it to some power. Of course, you get something that's 0 mod P. So we get the cardinality of set S is 0 mod P. All right, we're going to introduce now the group action. So far, so good. It's the first time we've considered a set of tuples, I think. And we're going to allow a group to act on those tuples in a certain way. So we're going to consider the group integers mod P. We're going to let the integers mod P act on set S as follows. First, a quick disclaimer. It says let K be an element of the integers mod P. Okay. Elements of integers mod P are equivalence classes. They're not themselves integers. But we're taking K here to interpret this as K is a representative of an equivalence class of Z sub P and choose K to be between 0 and P minus 1. This is certainly the way Fraley would deal with it, but we've been, up till now at least, more cautious with the notation when dealing with integers mod P. The elements of Z sub P are 0 bar, 1 bar, up through P minus 1 bar. So we've chosen one of those. Think of it, though, as simply a K, where K is between 0 and P minus 1. And we'll define the action of K on the tuple, so this is the element of the set, to be as follows. What we're going to do is we're going to take the first K of these elements and snip those off and move them over and place them on the right-hand side of the tuple. So when K acts on this tuple, we'll start with A sub K plus 1, and then get A sub K plus 2, up through A sub P, then A sub P sub 1, A sub 1, A sub 2, up through A sub K. So there's still all P terms there. We've just taken the first K of them from the front, chopped them off, and shifted them over to the right in the same order. Notice, by the way, if we were to interpret this as an equivalence class, hey, every multiple of P would leave these fixed. So we're okay in addressing this as K, a representative of Z sub P versus a K bar, and then dealing with all of that. I thought about writing the notes up to deal with the equivalence classes more hands-on, but it gets a little awkward to explain. But we're working mod P, and this is a p-tuple. So this is what it means to have those elements of Z sub P act on the tuple. If this actually is an example of group action, so we got to show that. So what we're doing is cycling the p-tuple around through k slots. Kind of imagine it as when it equals 1, we take this and cut it off and put it on the side. When k equals 2, we take the first 2 and cut them off and put them on the other side, and so forth. But is that, in fact, an example of group action? Well, first off, quick little algebraic manipulation. If AB equals the identity in a group, then B times A, we could write it as A inverse A times BA. Just put the identity on the left. Associativity allows us to group A and B. We got into this by saying if AB equals the identity, so I can replace that with the identity, and that simplifies to the identity. In other words, in a group, if the product of two elements A and B equals the identity, then the product of B and A also equals the identity. Here, we've got A1 through A sub P. These multiply together to give an identity in group G. So if we were to take the first K of these and think of that as element A, and take the second, P minus K of these, the second bunch of them, represent that as element B, we could reverse the order and we'd still get the identity out, as just argued in the first two lines. In other words, if I put B first, here it is, A sub K plus 1 through A sub P, and A second, A1 through A sub K, representing A and B is given here, we'll still get the identity. So when you do this group action of moving the things around, you still get an element of set S. It's still a p-tuple, and they still multiply to give the identity. So first thing, this alleged group action takes the ordered pair, group element, and an element of set S, one of these p-tuples, and actually gives out an appropriate type of p-tuple. So this is kind of like a closure property. So we've got the right setting. Does this action satisfy the two necessary properties related to the identity and the interaction of group action with the binary operation? Well, if you take the identity of Z sub P, that's just 0 bar. If 0 acts on a p-tuple, then it doesn't change anything. You simply get the p-tuple back. Right, it cuts nothing off and shifts it to the right, so that results in the same p-tuple. So we've got this type of behavior for all x in set S. So we're good on that part. Secondly, what if we take two group elements? Let's take K and K prime and Z sub P. Yeah, I know K bar and K prime bar, but take two elements of Z sub P. We need to show the binary operation, which is addition in Z sub P. The binary operation of those two elements acts on a p-tuple to give K prime acting on the p-tuple followed by K acting on the p-tuple. Well, this is fairly straightforward. What does K prime do? What does K plus K prime do? Well, we'll start at A sub 1 plus K plus K prime, and then get A sub 2 plus K plus K prime, up through the last term, A sub P. Then we'll pick up, actually this should read A sub 1, and we'll pick up A sub 1 through A sub K plus K prime. Well, we could shift this back by dealing with K acting on this tuple, and what we would then get would be A sub 1 plus K prime, have K act on that expression. That'll have us start not at 1 plus K prime, but 1 plus K prime. So K acting on this produces the previous line. And what we have here in this parentheses is K prime acting on the original tuple. So indeed, we get K acting on the action of K prime on the tuple. So the binary operation of addition interacts with this, this weird shifting thing in the appropriate way. When it makes sense, you're just adding things together. Modulo P probably needs to be said somewhere in there. You're just adding things together here in Z sub P. And you shift, and then you shift again. Of course, you get the sum of those shifts in an informal sense. So the second condition of group action is satisfied, and this thing we've defined really is an example of group action. All right. Remember, we just looked at S sub 0 in the first lemma. It was the x and s such that k star x equals x for all k in the group, in this case, z sub p. It's all the orbits of length 1. So we get a tuple, a1 through a sub p, to be in S sub 0 if and only if it's a tuple of constants. The tuples would have to be preserved. Let me forget the multiplication equals the identity thing for a second. The tuples have to be the same through the group action to be in S sub 0. For example, if k equals 1, that would produce the tuple a sub 2, a sub 3, up through a sub p, comma, a sub 1 is the last one. Well, we'd have to have equality of those correspondingly. The tuples being the same, which is what's required here, would require all the entries to be the same ultimately. So the only thing in S sub 0 is tuples of constants. Now, that's not an empty set because if we multiply the identity, take the tuple of all identities, multiply that out, you get the identity to the pth power, which is the identity. So that is, in fact, something in S sub 0. It satisfies the conditions. So the cardinality of S sub 0 is not 0. It's not empty. It contains that thing. We just saw in Lemma 2.5.1 that the cardinality of S sub 0 and the cardinality of S are congruent mod P. So that applies here. We've got group action as we needed from Lemma 2.5.1. S sub 0 is defined the same way in terms of the group action. So we saw above the cardinality of S was 0 mod P. So we conclude from the lemma that the cardinality of S sub 0 must also be 0 mod P. Okay, so it's a multiple of P. Not 0, though. We saw S sub 0 is non-empty by the argument up here. So S sub 0 has to contain at least P elements. Couldn't be 0, that we've shown. Smallest prime number is 2. So other than the constant tuple of all identities, there's another thing in S sub 0. Say A not equal to the identity, the tuple of all A's, for some A, I don't know what A is, but I know it exists by the counting argument, a tuple of all A's, which is in S sub 0. But then being in S sub 0 means if we'll multiply all those things together, we get a to the p power, we must get the identity out. There's your element right there that is of order p. Order at most p, we'd have to have a divisor of p, otherwise Lagrange's theorem will say something to that effect. Of course, p being prime, there are no other divisors except for 1, and we're not using p equals 1. So a to the p equals the identity, and A is an element of order P and generates a subgroup of order P. That's the plan in terms of addressing the Sylow theorems. Think in terms of subgroups of particular orders. Let me quote from a paper by Mio, The Mathematical Life of Cauchy's Group Theorem. This was printed in a History of Math journal, Historia Mathematica. The abstract reads as follows. So a little bit about Cauchy's theorem. Cauchy's theorem on the order of finite groups is a fixture of elementary coursework in abstract algebra today. Its proof is a straightforward exercise in the application of general mathematical tools. The initial proof by Cauchy, however, was unprecedented in its complex computations involving permutational group theory and contained an egregious error. So Cauchy messed up. A direct inspiration to Sylow's theorems, Cauchy's theorem was reworked by Richard Dedekind, G.F. Frobenius, C. Jordan, and J.H. Mackay in ever more natural, concise terms. Its most succinct forms employs just the structure lacking in Cauchy's original proof, the wreath product. I haven't dug into this in detail as to what the wreath product is. I rather suspect it's related to that p-tuples and the cutting things off, the group action that we used. On the second page of this paper, Mio also comments, Cauchy's theorem in permutation groups, which constituted the major conclusion of the 101 pages of an 1845 Cauchy memoir, appeared just before the posthumous publication of Galois' work in 1846. And these two publications together, of Cauchy and Galois, have recently been characterized as, quote unquote, the two sources that introduced group theory to mathematics. So it's, I normally think of Galois and Abel as introducing group theory to algebra. But here's a statement from this paper by Mio. So pretty fundamental stuff is what they're getting at. Just a quick little side note, the J.H. Mackay listed above in the abstract. I don't have too many connections to the algebra community, but J.H. Mackay's PhD advisor was the PhD advisor of the chap from whom I took graduate algebra, Paul Hill, in 1984-85 in Auburn. Paul Hill was at Auburn. William Ball, the PhD advisor, was also at Auburn when I was there. I think he retired while I was there pretty early on. Mackay, I think the connection with Mackay, I don't think that's through Auburn University though. But there's a little story on Cauchy's theorem. It's called Cauchy's theorem, even though Cauchy didn't present a correct proof of it. That's not unprecedented in the history of math. Okay, so on to Sylow's theorems. A group in which every element has order a power of some fixed prime P is called a P group. If H is a subgroup of a group G and H is a P group, then H is a P subgroup of G. So the P simply relates to the fact that the group or subgroup has an order, a power of that prime. They allowed the power to be 0. So strictly speaking, trivial groups, group generated by the identity, these count as P subgroups for all P as well, because E to the P to the 0, the identity to the first powers is the identity. And Sylow's results deal with P groups and P subgroups, and Sylow P subgroups before we're done. So we'll go through 4 little lemmas and corollaries that will lead us to a proof of Sylow's first theorem. So let's just go to the proofs and go through those one after the next without any need for intermittent commentary. Okay, corollary 2.5.3 states a finite group G is a P group if and only if the order of that group is a power of P. Not terribly surprising. Not the definition, strictly speaking, of a P group. Could take it as the definition since this is an if and only if result. If G is a P group and Q is some prime which divides the order of G, then G contains an element of order Q. Cauchy's theorem guarantees you that, as we just saw, a prime Q dividing the order of a group. There's an element of that order. But every element of G has the order of power of P. That was a definition of P group. So we'd have to have Q equal to P in that case. So the only prime divisor of the order of G is P. And so the order of G must be a power of that prime, P. Conversely, if the order of G is a power of prime P, Lagrange's theorem tells you the order of an element divides the order of a group. Well, then that the order of that element would have to divide this power of P, and the element itself would have to have some power of P order. So P group, if and only if the order is a power of P. I wouldn't be surprised you don't find references out there that give this as the definition of a P group. We've taken a different angle on it, but this is equivalent to our definition. Another result, the center, C of G, of a non-trivial finite group G contains more than one element. Okay, we might need to run back into section 2.4 here shortly. It says consider the classic equation of G. Okay, let's go back and look this up. We're expressing the order of G as the cardinality of the center plus a sum of indices of centralizers of X sub I in G. Let's run back and look at that. So note 2.4.A, I have to go back to this section. Here's where the class equation was introduced. This corollary 2.4.4 introduces the class equation. The cardinality of G is the sum of a bunch of indices of centralizers, the index of centralizers in group G. And we had played with that a little bit for just this occasion. We had gone through and said you can take the cardinality of G and write it as the cardinality of the center plus the sum of these indexes of centralizers of elements in G, where these X sub I's were chosen to not have an index of 1. And if we have an equivalence class that's of cardinality equal to 1, then you got yourself an element in the centralizer. Think of the definition of centralizer. If not, we'll pick those that have cardinality strictly greater than 1, pick those out. And they can be expressed in terms of indexes. That was in that corollary 4.4. And we had written the cardinality of G as a sum of indices. Just these are all of the indices that are of cardinality 1. We pulled those off and stuck them inside the center and counted them by using the cardinality of the center. So this is what we're talking about back in the proof. All right, so there's the equation. Definition of centralizer. Recall centralizer of an element X was the G in the big group on which we're having, I mean, that's eventually this will be group action. We've got conjugation producing simply element X back out. And it was introduced back there in terms of group action. All right, we have all of these indices in this summation to be of size greater than 1. Those that were of size 1 have been counted here in the cardinality of the center of G. That was the convention, the notation that was used in that note. We also said these indices divide the order of G. Excuse me, that was part of corollary 4.4 as well, part 1. So we're getting these, well, we're getting all of these indices to divide p to the n. The ones associated with the center, they're 1. So of course they divide p to the n, but these others do as well. So all these other indices divide the order of G. We've assumed G is a P group. So G is of order p to the n, as we saw in the previous lemma. So if this index divides p to the n, then p must divide this index because it's prime. And it's not 1, as we saw. So a reason to pull these off that are in cardinality greater than 1. G is a P group by hypothesis, stated up here. The previous corollary tells us then that G is a power of P. So P divides the order of G. Well, if P divides the order of G, P divides all these things, P must divide that thing. We've got P divides all these indices. Right here, P divides all the indices listed here. P divides the order of G, it was P group. P divides this, P divides that. Well, if it divides the left side, it must divide the right side. And if it divides all of these, it must divide that as well. So P divides the order, the cardinality of the center of G. There's something in the center of G. Right? This is the elements of G that commute with everything else. It always includes the identity. So the cardinality of the center is at least 1. It's not 0 in particular. So we've got P dividing this thing, and this thing is greater than or equal to 1. Well, then that thing has to have at least P elements in it. In fact, it must have a multiple of P elements in it. We were just trying to show it's got more than one element in it. It does. It's got more than the identity in it. If P is 2, then it has a second element. If P is 3, it's got 2 additional elements at least. But that guarantees us that there's something else in there, even when P equals 2. And there's your center contains more than one element. Another preliminary lemma. If H is a P subgroup of finite group G, so H is a subgroup of G and has order, power of P, then the index of H in the normalizer of H, we'll recall the normalizer here in a second, is congruent to the index of H in G mod P. All right. Technical difficulties. Slides to advance. There we go. Okay. Recall the normalizer is the normalizer of H and G is all G and H such that conjugation fixes H. So normalizer was defined as such. We could manipulate it. It looks reminds me of left cosets equal right cosets. It reminds me of normal subgroups, but this is defined for any subgroup H of G. So we're going to introduce a set and some group action. Let S be the set of all, say, left cosets of H and G, and let H act on S by left translation. First, S is the set of left cosets of H and G. How many of those are there? That's what the index symbol represents. So the index of H and G is the number of left cosets of H and G, or right cosets, same number, different sets potentially. So the cardinality of S is simply that by the definition of these index symbols. By the definition of set S sub 0 that we've encountered previously, we have, and I've made a bunch of equivalent statements and bracketed them off with parentheses. Is how this is written. So we get left coset XH is an S sub 0 if and only if that is fixed by the group action. That is, if we multiply, if we let H act on that left coset, left translation will give us HX, H, capital H. It'll have to fix that left coset. So you multiply on the left by H, we get the same left coset back out, and that must occur for all H in subgroup capital H. So we get this kind of behavior. That's what it means to be an S sub 0. We've just taken the group action and expressed it explicitly here. Now let's take this and manipulate it a little bit. We can multiply on the left both sides by X inverse. So it's a set equality, so be careful with these manipulations, but we've seen this before. And write this as X inverse HX. X inverse HX times capital H equals set capital H again. And this again holding for all H in group capital H. This occurs if and only if X inverse HX is in capital H, right? We're getting this to produce left coset H itself. Well, the only time I can multiply on the left subset H and get H back is when this is an element of H, behaviors of cosets, left cosets, if you like, as we've seen in the past. So element-wise, that means X inverse HX must be in capital H itself. Again, that's holding for all H and capital H. Since this works throughout, as H ranges throughout capital H, then I can replace that little center H with the whole set and express this as X inverse H, X equals capital H. Replacing the little h with capital H, since it's a for all little h and capital H. And what we've ultimately done is move some things around a little bit and absorbed this h somewhere along the way, picked up an X inverse, but all the details are spelled out right there. Well, we're going to get X inverse H, X equal to capital H if and only if X, H, X inverse equals H. And the change is, here we've got the X inverse on the left and the X on the right. Kind of think of multiplying both sides by X and X inverse on the appropriate side. Here we've got X on the left and X inverse on the right. So we've reversed the orders of these, multiplying, say. And we get X, H, X inverse equals H. Well, that occurs if and only if X is in the normalizer of H. After all, that's what the normalizer is. It's elements of big group G, such that that element H, that element inverse equals H. Same thing we've got down here, except down here we've got an X symbol instead of a G symbol. But you got yourself an element of the normalizer. So we had XH is a left coset in S sub 0, if and only if X is in the normalizer of H. So there's the same number of these left cosets of X and S sub 0 as there are these X in the normalizer of H. That is, the cardinality of S sub 0 is the number of left cosets with X in N sub G H. I could draw a cardinality conclusion from that. Normalizers are themselves groups, subgroups. See Theorem 2.4.2, we talked about stabilizers. So what the normalizer is a stabilizer under a particular group action. It's group action of conjugation on the set of left cosets of H. But here's the documentation to say this indeed is a subgroup. H is a subgroup of the normalizer. I take anything in H and it's going to behave an appropriate way to be an element of the normalizer. Things in H just get absorbed by H. So we can look at the number, the index number, let's say number, everything's finite here, the number of cosets of H in the normalizer of H. The number of left cosets of H in the normalizer. And we see S sub 0 was exactly that, number of left cosets of H in the normalizer from the previous slide. That can be written in terms of these index symbols. So S sub 0 in cardinality equals this index. All right. We know the cardinality of S is congruent to the cardinality of S sub 0 mod P. Previous slide, asterisk. Let's look back. We had the cardinality of S was equal to this index. Here we've got the cardinality of S sub 0 is equal to that index. So this index and this index must be congruent, mod P. Let's look back one more time. Asterisk was the cardinality of S equals this index, index of H and G. Let's look back, and there it is. Cardinality of S is the index of H and G as claimed. Substitute in, and that gives us the mod P claim. All right, I think this is our last corollary, and then we'll go through the proof of Sylow's theorem, Sylow's first theorem. If H is a P subgroup of a finite group G such that P divides the index of H and G, then the normalizer of H and G is not equal to H itself. Okay, P divides the index. We hypothesize that. So the index is 0 mod P. The lemma we just saw told us that this index, H and the normalizer of H, is congruent to that index, mod P. So this index must be 0 mod p as well. Normalizer of the index of h in the normalizer greater than or equal to 1. It has to contain at least one coset. Based on the identity, there's a coset of h right there that's contained in the normalizer. H itself is contained in the normalizer. So we must have this index is at least p. It's not 0 is what we're showing here. It must be 0 mod p, so it must be a multiple of p, a non-zero multiple of p. So it's at least 2. That is the index of h in the normalizer of h must be strictly greater than 1, because 1 isn't prime. It's at least 2. And if that's the case, then these can't be equal. The only time you get equals 1 is when this and this are equal to each other. When h equals the normalizer, then we'd only have one coset. So that can't be the case, and we get this conclusion here.